Okay, so we're going to talk a little bit now about reaction rates. Now, I don't know about you guys, but at this point, when I think about reactions, I think about equations. So, for instance, something really simple like, a couple of diatomic hydrogens and a diatomic oxygen give me a couple molecules of water, right? Really, really basic. But what we don't always think about is the rate at which reactions occur. So that's what we're going to be focusing on today. So first off, what is a reaction rate? Well, you pretty much just want to think about it as the rate at which something is either being created or consumed, right? It's the reaction rate is based on the rate of either the appearance of a product or the disappearance of a reactant. So we're usually going to express that in terms of a change in concentration. So a change, we're measuring a change in concentration and the rate at which that occurs. So for instance, you could look at the rate at which we are using up our diatomic hydrogen, or you could look at the rate at which we are creating our water, and either one of those would give you the reaction rate. One of the things that you want to be thinking about is, okay, well, what do I have that's actually reacting here, right? So for instance, if I had something that was like ionic in an aqueous solution, that's going to be a pretty easy bond to break. So it's going to be a pretty fast reaction, right? Versus if I had like a really strong covalent bond, that would probably take a lot longer. It would probably be a pretty slow reaction. Think of it as the difference between like splitting up a block of salt or a sugar cube, right? Something that's not held together terribly well, and trying to split a piece of wood, right? Something, essentially, the more closely and the more strongly things are bonded together, the longer it's going to take for a reaction to occur, because the longer it's going to take to break those bonds. Another thing you're going to want to think about is the surface area of your item. For instance, let's say you've got an onion and you're trying to cook your onion. Yeah, I mean, let's face it, all cooking on some level is chemical reaction, right? So if you've got, let's say, I apologize in advance for my drawing. As you all know already, I'm the awful at drawing, right? But if I am trying to cook some onions over, let's say, like a gas range or something, right? Certainly, if I just plop my whole onion in there and I don't chop it, it's going to take a lot longer to cook than if I were to take the same onion, put it in the same pot, but chop it up first, right? And the reason for that is because guess what? When I chop it up, suddenly I've got a lot more surface area to work with than if I'm just dealing with this big old blob of onion, right? So this is just like sort of a macro representation of a micro problem. The less surface area that we have to work with, the longer reaction is going to take. The more surface area that we have to work with, the more something is sort of broken down, the easier it is going to be to get that reaction to take place and to get it to take place quickly. Another thing to take into account is concentration. Since all reactions are somewhat probabilistic, right? You got a couple of hydrogens hanging out over here. You've got an oxygen hanging out over here, right? And ultimately all that reaction is the likelihood that these guys are all going to bump into each other. right? Obviously, the more of it that you have in a solution, the more likely it is that they're going to bump into each other and get that reaction to occur. So it shouldn't be too much of a stretch to think about concentration as being directly proportional to the rate of the reaction. So in other words, the reaction will happen faster if you have your reactants in greater concentration, because it's just more likely that they're going to run into each other along the way. Of course, temperature is going to be a factor here as well. As we see increases above room temperature, we generally are going to see reaction rates either doubling or tripling, right? And again, if we think back to the laws of sort of kinetic energy, right? That'll make sense because we know what happens as temperature increases. Well, temperature is really just kinetic energy, right? So kinetic energy is going to increase. That essentially means your molecules are moving more and more quickly. Your particles are moving more quickly, right? Particles moving more quickly means, you guessed it, they have a greater likelihood of running into each other, right? So greater temperature means particles, it'd help if I spelled the word particles correctly, moving faster, which you guessed it means, in general, a higher reaction rate. And finally, catalysts. This is probably a word you've heard before. We're going to talk a little bit more about catalysts in the later videos, or rather, Sal Khan is going to talk a little bit more about catalyst in the videos listed later on in this unit. But essentially that catalyst can help to increase the rate of the reaction. It can help to facilitate the reaction by making the activation energy a little bit lower. So obviously, if you have a positive catalyst, that will also affect the rate of your reaction. Okay, so here we have all of the 5 basic factors that can affect the rate of your reaction. I'm going to let Sal Khan tell you a little bit more about activation energy and entropy and enthalpy, and then I'm going to be back for the final video to talk to you a little bit more about the reaction rate law. I know you guys are excited. I am too.